Hi, so I found this question in paper 1 of the HL paper of May 2018. And this question's from section B, so that's the harder section. And it's worth 17 marks, so that's quite a bit. That's 17% of paper 1, so worth quite a lot. So it's important to get it right. So in this video, I'll be walking through how I would approach this problem. But first, I recommend that you pause the video and try to solve it yourself. Right. So let's get started with the question. They've said that f of x is this business right here, and x is real, x is not 0, and we need in part A we need to find the local minimum, the coordinates of the local minimum. So, so the local minimum would look something like this, and the gradient would be 0 at that point. So the first derivative, which gives the gradient, would equal 0. Now we could use the quotient rule to differentiate this function, but I think it's a lot simpler to simplify it. I'll explain why later. So say we try and simplify this, y equals 2 over 2 to the x cubed minus 3x to the 5 over 2x cubed, which equals x to the minus 3 minus 3 over 2x squared. Now, I think this is a lot simpler to just normally differentiate rather than using the quotient rule here, because it's a lot quicker. And often people have timing issues on paper 1. So it helps if you can find ways to solve problems quicker. So to differentiate this, dy over dx equals, we bring that down here, minus 3x to the minus 4, minus 3x to the 1, so just nothing. And we know that equals 0, because here. And we just solve this equation. We can divide both sides by x, because x is not equal to 0. So minus 3x to the minus 5 minus 3 equals 0. We can also divide by minus 3. So we get x to the minus 5 equals minus 1. And then, so that's just 1 over x to the 5 equals minus 1. So x to the 5 equals minus 1. So x equals minus 1. Now we've got x, we need to find the y coordinate. So y equals at x equals minus 1. Y equals, we can just see here, 2 minus 3 minus 1 to the 5 over 2 minus 1 cubed, which is just 2 minus 3 minus 1, 2 minus 1, so that's just 2 plus 3, so that's 5 over 2 minus 1, so that's just minus 2. So that's just minus 5 over 2. So the coordinates would be minus 1 from here, and minus 5 over 2. So that's the y coordinate, minus 5 over 2. So we're done with part A. So let's move on to part B. Part B asks us to show that there's exactly one point of inflection. So we need to prove that there's one and only one point of inflection. And the two conditions for a point of inflection are that the second derivative needs to be 0. And, the sign of the second derivative, not the third, the second derivative changes sign and if the second derivative changes sign, that means that the rate of change of the second derivative is in 0, and the rate of change of the second derivative is just the third derivative. So f triple dashed is not equal to 0. And if f triple dash was equal to 0, that's not an inflection point anymore. That would be an undulation point. So that's a point where even the rate of change of the second derivative is equal to 0. So that would sort of graphically look like a flat sort of section of the graph. So for example, in y is x to the 4, the second derivative is 12x squared, so that would be 0 when x is 0, and when x is 0, f triple dashed, which is 24x, that will also equal 0, so that would make it an undulation point rather than an inflection point. Even though the second derivative is 0, it's still not an inflection point because the second condition is not satisfied. So for the question, let's find the second derivative. So that would be plus 12x to the minus 5 minus 3. And we know that equals 0 at the inflection point. So we can just solve for x. So we divide by plus 3. So we get 4, we get minus 1. So we get 4x to the minus 5 equals plus 1. So x to the minus 5 equals 1 over 4, which implies that x to the 5 equals 4. So you just invert both. And we get x equals 4 to the 1/5. So that's only one solution. So this equation only has one solution, and that means that, and we still don't know yet if the point where x equals 4 to the 1/5, we don't know if that is an inflection point or not. It only may be an inflection point because it satisfies the first condition, but we don't know if it satisfies the second, so we still need to check that. So only one solution would imply that there's at most one inflection point, but we don't know. It may also be 0. We don't know if this point is an inflection point. So this was the first part. Then let's check if the second condition holds true. So let's find the third derivative. That would be minus 60x to the minus 6, and this is constant, so we just leave it. And at x equals 4 to the 1/5, f triple dashed of x equals minus 60 times 4 to the 1/5 to the minus 6, so that would just be minus 6 over 5, and that is obviously not equal to 0. So the second condition holds true. So we know that this point is, so x equals 4 to the 1/5 is an inflection point. So we know that there's at most one inflection, and that one point that may be an inflection is an inflection. Therefore, there is exactly one inflection point. And we need to write this final conclusion statement because it's a show that question. So there's this one last reasoning mark for which we need to write the concluding statement. So that's part B1 done. So let's move on to part B2. In part B2, so I've written f of x and the value of x at the inflection point here for reference because it'll be required in this question, in this part. So part B2 says, let the coordinates of the inflection point be 2 to the a, comma, b times 2 to the minus 3a. And a and b are rational numbers, so that's this weird Q here that I tried to draw. And we need to find the values of a and b. So we know that at the inflection point, x is this here. So we can say that 2 to the a equals 4 to the 1/5. Now we can try and get both sides with the same base number. So we can equate the powers. So 2 to the a equals 2 to the 2. 4 is 2 squared. So 2 squared to the 1/5. Which means that 2 to the a equals 2 to the 2/5. So a, we can just equate the powers. So because the base is equal. So a equals 2/5. And then to find b, we try and find the value of f of x at x equals 4 to the 1/5. So f of 2 to the 2/5, so that's the same thing, right? Equals 2 minus 3 times 2 to the 2/5 to the 5th to the 5th, or 2 times 2 to the 2/5 times 3. So that equals 2 minus 3 times, so 2 to the 2/5 times 5 equals 2 squared, which is just 4. And 2 times this thing here, so that would be 2 to the 6 over 5. Yes. And we just evaluate that, so that would be 2 minus 12 over 2 times 2 to the 6 over 5. So we can divide the numerator and denominator by 2. So 2, 1, 6. So we get 1 minus 6 times 2 to the, so I'm taking this up, so just negate that. 2 to the minus 6 over 5, which is just minus 5 times 2. So we can see in the question it's b times 2 to the minus 3a, so we need to get it in that form. So this would be our b, and let's see if that fits in, if we can use the same value. So minus 6 to the 5 is just minus 3 times 2 to the 5, and 2 to the 5, 2 to the 5 was our a, so that fits in well, and minus 3, so it's of that form. So that equals b times 2 to the minus 3, and we know a from here that it's 2/5. So this bit is equal, and we can equate these two. So b equals minus 5. So we found the answer. So the answer is just a is 2/5 and b is minus 5. So let's move on to part C. And part C asks us to sketch f of x and show the maximum point and inflection point. And this is what 4 marks, which means that there are 4 marking points. So I will let you know what the 4 marking points are. But I think it's useful to know what like sketch questions are worth in terms of marks, because we know that they're looking for 4 things, and we can make sure we are showing those 4 things. So in part A, we found the maximum point to be -1, minus 5 over 2. And the inflection point, we found that in part B2 as 2 to the 2/5, -1 times 2 to the minus 3 times 2/5. So I would first look at which quadrant these points would be in. So this is negative and this is negative, which means it's in the 3rd quadrant. So minus in x, like on the x-axis, and minus in the y-axis. I think it helps thinking of it in that way, because I can never remember quadrants. So minus and minus. So it's going to be somewhere here. I'm not drawing it to scale, but something like that. You get the idea. So this would be your max point. And since it's a max, it would be sort of like that. So the shape would be like that. That would be the max. And the inflection point, so this 2 to the 2/5 is a positive number. And -5 to the times 2 to the any power. So 2 to the any power would always be positive. And that's a positive number multiplied by a negative number would give me a negative number. So the inflection point is so positive x and negative y. So it's in this quadrant. So let's say it's somewhere here. It's not to scale. And since it's an inflection point, it's going to look something like that. So let me draw that. And f of x was not defined at x equals 0. So it makes sense if there's an asymptote here, you can verify by checking the values. So this would be our sketch. So the 4 marking points would be with the 2 quadrants. So the max point is in the correct quadrant and the inflection is at the correct quadrant. And 2 points for the shape. So 1 point for the shape of this and 1 point for the shape of that. So that would be 4 marks. And we're done with the entire question. Thanks for watching this video. Hope it helped. Please let us know if you have any question requests or any feedback in the comments below.